In 1996, the astronomical community was abuzz with a revolutionary new concept. A committee of eminent astronomers, led by Alan Dressler, convened and put forward an unprecedented proposal: the development of a space telescope capable of observing the universe in infrared light. This telescope, unlike any before it, would be able to observe through the obscuring dust and gas clouds that would otherwise obscure the view of an ordinary telescope. Perhaps most importantly, the telescope would be able to look further back in time than ever before, unlocking the secrets of the early stages of the universe. The recommendation set in motion a series of events that would ultimately lead to the creation of the most powerful space telescope mankind has ever observed, the James Webb Space Telescope, or JWST. This revolutionary concept generated considerable enthusiasm and ambition within NASA and the astronomical community. The concept of building a telescope capable of observing in the infrared wavelength, which allows the observation of phenomena invisible to the human eye, promised to expand our understanding of the universe in ways previously unimaginable. Infrared light is particularly useful for astronomical observation because it can penetrate the thick clouds of dust and gas that often obscure the view of distant celestial objects. Traditional telescopes, such as the Hubble Space Telescope, observe primarily in visible and ultraviolet light. While these wavelengths can reveal much, they are limited by what they can penetrate. Infrared, however, gives scientists the ability to see through these cosmic veils and peer into previously hidden regions of space. This capability allows the James Webb Space Telescope to provide a much clearer and more comprehensive view of the universe. In 1997, NASA formally agreed to fund studies to explore the feasibility of building such a telescope. 3 teams of scientists and engineers, representing both the public and private sectors, were assembled to assess the technical and financial requirements for realizing this vision. The results were encouraging. All 3 teams agreed that the telescope could indeed be built. This marked the beginning of the journey to make this idea a reality. By 2002, NASA had selected the main teams responsible for building the telescope's main instruments, and an advisory group of leading astronomers was formed to oversee the telescope's construction and scientific objectives. The telescope would not be a typical astronomical instrument. It would be an observatory operating in a deep space orbit far beyond the Moon, with a diameter of more than 4 meters. The telescope would be optimized for infrared light, making it possible to study distant stars, nebulae, and exoplanets in ways never before possible. Its advanced capabilities would not only expand humanity's view of the cosmos, but also facilitate deeper exploration of space and time, shedding light on the universe's earliest phenomena. In 2004, construction of the James Webb Space Telescope, JWST, began on schedule. However, the construction of this telescope presented a unique set of challenges. Unlike the Hubble Space Telescope, which orbits relatively close to Earth and can be serviced by astronauts, the James Webb Space Telescope would be positioned at an unmanageable distance. This meant that every component of the telescope had to be carefully designed and tested to ensure that it could operate flawlessly for years, without the need for repairs or upgrades. In the event of a malfunction, there would be no way of rectifying it, putting considerable pressure on the engineering and scientific teams responsible for the project. One of the most important elements of the telescope was its primary mirror, which was responsible for collecting the light from distant stars and galaxies. To capture enough light from the faintest and most distant objects, the mirror had to be of considerable size, significantly larger than that of Hubble. The solution was to design a segmented mirror made up of 18 hexagonal segments that would work as a single unit. Each segment had to be precisely aligned to ensure that the telescope could focus light effectively. The mirror segments were coated with a thin layer of gold, which is highly effective at reflecting infrared light. However, the design and testing of these mirrors presented a significant challenge. They had to be lightweight, yet robust enough to withstand the extreme conditions of space. By 2012, construction of the various components of the telescope was well underway, and the process of assembling and testing these components began. The team encountered a number of technical challenges throughout the construction process. By 2013, however, the sunshield layers were already under construction. The sunshield plays a crucial role in the telescope's operation, protecting the telescope's instruments from the intense heat of the sun and ensuring that they maintain an optimal operating temperature. Infrared observations require a very cool telescope, as even minimal heat can interfere with the infrared signals it is trying to detect. Over the following years, the telescope underwent a series of rigorous tests to ensure it could withstand the extreme temperatures and vibrations it would experience during launch and in space. Each of the 18 mirror segments was meticulously attached to the telescope's backplane, the structural element responsible for holding them in place. By 2017, all of the telescope's components were fully integrated and undergoing rigorous testing at NASA's Johnson Space Center in Houston, Texas. Despite the adverse effects of Hurricane Harvey in Houston that year, the team persevered and completed the final stages of environmental testing in a state-of-the-art thermal vacuum chamber that replicates conditions characteristic of deep space. After decades of meticulous planning, construction, and rigorous testing, the James Webb Space Telescope is finally ready for its first launch. On 25 December 2021, at 7:20 a.m. Eastern Standard Time, the telescope was launched aboard an Ariane 5 rocket from the European spaceport in French Guiana. The world watched as the telescope began its interstellar journey. The atmosphere was palpably tense, with decades of work, billions of dollars, and countless hours of effort riding on the success of this mission. The launch went off without a hitch, and the telescope began its journey to its intended destination, a point in space known as Lagrange Point 2, L2, about 1 million miles from Earth. As the telescope moved through space, it began the complex process of unfolding and deploying its many components. Unlike Hubble, which was relatively simple in its design, the James Webb Space Telescope was constructed in such a way that it had to be folded up to fit inside its rocket. Once in space, the telescope had to deploy its mirrors and sunshield in a precise sequence. First, the solar array would deploy, providing power to the telescope. Then the sunshield, which is about the size of a tennis court, was carefully deployed and tensioned. This sunshield is made up of 5 layers, each as thin as a human hair, and had to be deployed with precision to ensure that the telescope remained at an optimal temperature. Next, the secondary mirror was deployed to help focus the light collected by the primary mirror. Finally, the 2 lateral extensions of the primary mirror were deployed, completing the telescope's full configuration. On the 30th day of the mission, the James Webb Space Telescope reached its final orbit at L2, and all systems were found to be operational. The telescope was now ready to begin its mission of observing the universe in unprecedented detail. This raises the question of how exactly the James Webb Space Telescope works and how it differs from other telescopes such as Hubble. Its primary function is to observe infrared light, while the Hubble Space Telescope observes primarily invisible and ultraviolet light. The James Webb Space Telescope, JWST, is optimized for infrared observations. This will allow JWST to observe celestial objects that are too cool or too faint to be seen in visible light. Distant galaxies, newly forming stars, and planets in the early stages of development all emit most of their light in the infrared spectrum. By capturing this light, the JWST can shed light on the formation and evolution of these objects. One of the most fascinating aspects of JWST is its ability to look back in time. The time it takes for light to travel from distant celestial objects to Earth is a function of their distance. So observations of galaxies at great distances in the universe provide images of these objects as they existed billions of years ago. JWST's advanced infrared instruments will allow observations of galaxies that formed just a few hundred million years after the Big Bang, providing insights into the earliest moments of the universe. The telescope's large mirror array and advanced imaging equipment will enable it to capture highly detailed images of distant objects. The near-infrared camera, NARCam, and the mid-infrared instrument, MIRROR, will detect faint infrared signals, while the near-infrared spectrograph, NARSPEC, and the fine guidance sensor, FOGAS, will analyze the composition of distant stars and galaxies. Together, these instruments will enable unprecedented studies of the universe. One of the main goals of JWST is to study the formation and evolution of galaxies. By observing galaxies at different stages of their development, scientists can build up a comprehensive picture of how galaxies form and evolve over time. The telescope's infrared capabilities are particularly useful for this purpose, as the light from distant galaxies is often stretched to longer infrared wavelengths due to the expansion of the universe. This phenomenon, known as redshift, makes it difficult for visible light telescopes to observe distant galaxies. But the JWST's infrared detectors are uniquely suited to this task. The telescope will also provide a unique opportunity to study the formation of stars. Stars form in dense clouds of gas and dust called stellar nurseries. these clouds are often opaque to visible light, making it difficult to observe the early stages of star formation. However, infrared light can penetrate these dusty clouds, allowing scientists to gain unique insights into the inner workings of these stellar nurseries. By studying these regions, scientists can improve their understanding of how stars form and evolve. As well as studying galaxies and stars, the James Webb Space Telescope will also be used to study black holes. On some black holes, particularly supermassive black holes at the centers of galaxies, are surrounded by vast amounts of gas and dust. These regions emit primarily in the infrared spectrum, making JWST an ideal tool for studying the structure and behavior of these fascinating cosmic phenomena. By studying galaxies, stars, and black holes, the James Webb Space Telescope is expected to revolutionize our understanding of the universe. By peering deeper into space and further back in time than any previous telescope, JWST will unlock the mysteries of the origins and evolution of the cosmos, giving humanity an unprecedented glimpse into the earliest chapters of the universe.